Hello, everybody. Welcome to our webinar. It's a joint webinar of LightTrans and Dynado, and the topic is robust design optimization. My name is Michael Kuhn, and the presentation is given together with Stefanie Kunert from Dynado.
Hello, everybody.
So let's start with some technical remark. In the GoToWebinar software, you have the opportunity to raise your hand and to ask questions to us also during the webinar, and we will try to answer these questions in between or after our presentation. Here's a short outline which you know already from the announcement of the webinar. We will start with a very short introduction to VirtualLab, overview of VirtualLab, because our listeners are also from Dynado and not just from LightTrans. We will, in the main part of the webinar, discuss the robust design optimization concept with the different steps of understanding your design problem, improving this design, and ensuring quality. And in the second part of the webinar, we will also give two examples with one beam splitter and one grating polarizer. Let me start with some remarks about LightTrans. You can read here the main facts. So what is important? We have distributors all over the world, so you can contact these local distributors also to get your questions answered. The main product, of course, is VirtualLab's optical design software, VirtualLab Fusion, which is being developed now by the company Photonics. And LightTrans offers all the support around this software, including trainings, of course. And what we also offer are the engineering services. So if you do not want to solve your design problem by yourself, then we can help you to deliver the design results and also the optical components, so fabricated components. There are a lot of applications for VirtualLab, especially in the field of laser systems, also including pulsed laser systems and laser resonators. And we have also solutions for illumination systems, so for design tasks in illumination systems. Some examples are given here, which includes the design of beam splitters, the design of gratings and diffusers, and also applications for homogenization systems for LED light sources also. So what is special about VirtualLab is really that we have started more than a decade ago to offer physical optics modeling, and recently we have also added a ray tracing engine to the software, and both together are very, very strong to tackle problems from these different fields of applications. And as you know, this physical optics modeling is really required to overcome the limitations of classical ray tracing methods. So, and all this is in one software. So, as you see here, you can compute with rays, you get these dot diagrams. And if you switch to field tracing methods, of course, you handle the complete electric field and magnetic field. And here's the example, a Y component of the electric field in a focal region. So this is very nice. You can cover many effects as polarization, diffraction, and also coherence effects. Partial coherent light sources can be considered. And one part of this is also the rigorous grating analysis. So if you have gratings in your laser systems or standalone gratings, you can analyze them, and you see the efficiencies of a grating under different angles of incidence. All the simulation techniques are, of course, the basis for tolerancing and optimization. There we have again several tolerancing tools, especially the parameter run allows you to scan parameters in linear mode or also in Monte Carlo modes. And VirtualLab always has a programming interface where you can customize all your structures and also the parameter selection for such experimental series. Optimization tools include tools for local and global optimization, and also the inverse Fourier transform algorithm, which is applied for design of diffractive optics, for example. So nevertheless, these are some kind of standard tools, and we have been aware that there are also some limitations with that, and we are also aware that we as Lightrans and the development of VirtualLab has the expertise in optical simulation and in optical design, and certainly less expertise in the field of optimization algorithms. And that's why we have started a cooperation with Donato company, and we have established a software interface between VirtualLab and the software optiSLang. And this provides you a powerful software environment for solving optical design tasks. And this is what we want to introduce in this webinar. You see some screenshot of the export functionality in VirtualLab, and this can then be imported as information to optiSLang, which will be discussed later also. So after all, the application of optiSLang allows you to extend the optimization capabilities of VirtualLab. Our presentation here will show you the basic principles. We present you some first application examples which should emphasize these features, and we invite you also to discuss with us your requirements, which will finally lead to more advanced examples also. And so what you will see here are the first steps, also with respect to the examples, and it's certainly not the limit what you really can do. And if you would like to start, we offer you some common projects with us, such that we can support you in an optimal way to start your projects. So this leads us to the introduction of optiSLang, and here I hand over to Stephanie.
So I'd like to show you now the basics of robust design optimization and some examples in optics, of course. So our company, Donato, was founded in 2001, and now we are 50 to 60 employees in Weimar and Vienna. And actually, we come from computer-aided engineering, mainly in the mechanical engineering, and that's why especially Daimler and Bosch were asking us to develop the software and to include a lot of features. Therefore, our software is really for industrial applications. So we do software development and consulting in the field of computer-aided engineering, and our main specialty is the sensitivity analysis, optimization, robustness evaluation, and the robust design optimization. What this means, you will see, and I mainly want to focus briefly on the requirements for real world applications. So as you all know, is that your virtual prototyping process needs a lot of computational resources, and so there is a need to increase the amount of necessary runs too much. Also, the physical phenomena might be coupled, like mechanics and optics. And nonlinear and high-dimensional relations are of interest. And you also might need to deal with failed designs when you cannot really calculate a design. And if you might have a lot of parameters. So to deal with all these hindrances, you can use optiSLang because all of these real-world application scenarios can be calculated with optiSLang. So our tool, optiSLang, is for general purposes, especially in the field of design and data exploration, calibration, sensitivity analysis, optimization, robustness evaluation, reliability analysis, and the whole thing is called robust design optimization. Our software uses predefined workflows, algorithmic wizards, and very robust default settings. And therefore, it's very easy and safe to use. So what robust design optimization and this concept means, I will show you now. You will always start with a sensitivity analysis to understand your design. Afterwards, you might do an optimization, because the sensitivity analysis will help you to find out first which parameters are important and will have a real impact on your responses. And you will also find out how your objectives are in conflict or not. And with this information, you can start the optimization as a second step. Because then your optimization will be very efficient with this knowledge, because you reduce the parameter range and amount, and you can then define very sufficient objective functions. After you have obtained your optimal design, you can do a robustness evaluation in order to find out if your design is really robust against input variations. So that means that you can find out which input variation is critical, referring to your robustness criteria. And you can also find out which input tolerance you might widen in order to save money. To show you a little bit more in detail what this strategy of robust design optimization means. You might start as a first step with the calibration of your system by matching experiment and simulation. After this, you can understand your design by using Metamodels to approximate the solver response, and also to use our post-processing, which is very powerful. And then you improve your design systematically by reducing the input parameter amount and range, and by defining reasonable objective functions. And then you can ensure the quality of your designs by identifying critical input tolerances, and also you have the potential to widen tolerances. And to reduce the the influence of input tolerances, you might do a coupled robust design optimization, which is an optimization and robustness analysis in one loop. And this is really very sophisticated, but easy to do in optiSLang. So after all, you have a very effective improvement of your product performance. How this is done, or what it means, is presented here as a house. So the basis of this house is this computer-aided engineering process. In this case, it means here is the VirtualLab integration process. And this looks like that in optiSLang, that automatically this workflow is set up by using a solver wizard. So it means it uses this input file of VirtualLab, this parameters XML, and this BAT file then is reading this input file. So VirtualLab is actually calculating the results, and then these results will be read by optiSLang and analyzed. And you can imagine that this is a loop you can do many, many times for a lot of samples and designs. So finally you will have a jar of designs that is, for example, a sensitivity analysis or an optimization. So everything is automatically done. And if you are an advanced user, you might build up very sophisticated workflows that could look like that. For example, to couple optical and mechanical studies. In this case, here we have a geometry tool. Here also ANSYS Workbench has mechanical tools included. And here MATLAB as a post-processor. You can couple any tools in a workflow, and once established such a workflow, you can use it for any application, for sensitivity analysis, optimization, robustness analysis. So everything is automated, and it can also be coupled to a PLM data management system, or you can also handle your jobs, your recalculating jobs very easily with optiSLang. After you have established that, here are also some integrations again shown. So, but these are only some of them. The easiest way to connect a solver is to use ASCII file-based solvers, which can be executed in batch mode. So you can actually couple any solver. So after the integration of the process of VirtualLab, we can now do the sensitivity analysis, which means we will find out the sensitivities of the inputs with respect to the important responses. And we can estimate the variation of the responses. Also, we can estimate the noise of the underlying model, and we will understand better and verify the dependencies between input and response variation. And of course, what is very important is to analyze if the objectives are in conflict. The requirements for industrial applications I have already mentioned before. So this is a flowchart of the sensitivity analysis. So the heart of it is this design of experiment, which means you have distributed your designs in your design space in a particular way, usually homogeneously. And based on this design of experiments, you can calculate now these inputs by the solver, which is here VirtualLab, and to get your output. So you will have a data pair of inputs and outputs that will be calculated by regression methods. So you will get, for example, a sophisticated Metamodel, which is included in optiSLang. And this Metamodel can or will show you the relationships between inputs and outputs. So you are able to understand which input indeed has an influence on your output and how high or how strong this influence is, which is represented here. And this is actually the sensitivity evaluation. As you have seen, this Metamodel, which is the basis for the sensitivity analysis, is indeed a very powerful algorithm. We call it Metamodel of optimal prognosis. And this Metamodel is actually the approximation of the solver output by a fast surrogate model. So what this algorithm actually does, it reduces the input space and only uses the best variable subspace automatically, which means you don't have to consider which input parameters are really having an impact on your responses. Everything is done automatically. The second thing is that also the best metamodel is so automatically selected. So the best approximation model is chosen, like if it's a polynomials, moving list squares or Kriging model. So this you don't have to choose by hand. Always the best fitting will win. And this fitting is estimated with a coefficient of prognosis. So, which means we have a particular coefficient that really is able to help you to get models that can also predict points in the design space, like shown here maybe, where no point has been calculated, no design point, but the model is able to approximate it perfectly, which is verified with this coefficient of prognosis. So you actually get a nice model to understand input and output, and also based on this model you get such a chart where you can see which inputs really have an influence and how strong is the influence. And this MOP, this metamodel, can be used for pre-optimization, for example. Now we are in the optimization part. So as you can see here, our input parameters are reduced by the sensitivity analysis to the really important input parameters. And now you can use this reduced data set or reduced input parameters to do the optimization. And for this optimization, you can use in the first step a metamodel of this metamodel of optimal prognosis. Usually you would do only the second step, this optimization based on the solver, like VirtualLab. But here, this is a unique feature of optiSLang, that you can pre-optimize your system with this metamodel in case of that you have very long solver response times. And then this will save you a lot of time. And how this optimization is done, so we have a lot of available algorithms, but not the amount is important, the quality is important, which means we have benchmark algorithms that, so you have for any application a suitable optimizer, a suitable algorithm. For example, for the gradient-based methods which are available are mainly nice for very continuous variables and low noise. And so they are restricted, but they are very fast and give you they go really close to the optimum. But if you have more variables, like up to 20, but because the gradient-based methods work like up to 5 or 6. If you have more variables and also maybe a noisy solver response, this adaptive response surface method is the method of choice. And if it's getting even more sophisticated, like that you have very high numerical noise and nonlinearities and a very high number of variables, this nature-inspired optimization methods are the best. To these belong the genetic algorithm, the evolutionary algorithm, and the particle swarm optimization. But you don't have to worry about the choice of the optimizer, because in optiSLang we included decision tree to select the optimizer, which is the most suitable one. So we have some intrinsic information available about the number of parameters and the type of parameters, and you as user can now select how about your solver noise, how high it is, if you have failed designs, and so on. But this information you will find out easily by the sensitivity analysis. And based on this information, now you will get a traffic light, and your choice will be, in this case, this gradient-based method. After getting this best design, you can evaluate the robustness of your design. And for that, you can go again step by step using this optimized design and give it to optiSLang, where actually a kind of quite similar, like a second sensitivity analysis is performed, but here different input parameters are selected. You don't only use the design parameters you have chosen before. Here you include also the parameters that really influence your design concerning the robustness, which means there could be environmental factors like temperature, or also loads, or whatever will really influence your design. And this robustness evaluation is based also on the solver response. And how you define your robustness depends, of course, on your application. The most famous one might be this definition by the sigma level. So you have a distribution of your response around the optimum, and you want that a particular limit is not exceeded. And this limit to exceed the limit, there is also a failure probability that you don't want to exceed, or that should be small, let's say. So another kind of definition is the robustness in terms of the objective. So you can see here that this optimum is more robust compared to that, because your variation in x direction will lead to a quite small variation in y direction, compared to here where small x direction based variation will lead to a higher y direction variation. And you can imagine that you can define whatever you like to define your robustness analysis in optiSLang. To do the analysis, it is very similar to the sensitivity analysis. The difference is that at the beginning you define the robustness space, as I mentioned, that you define your parameters, not only referring to the inputs that you defined in the design space, but you also can add environmental factors and loads. And then you define the scatter range and distribution, and you can also define correlations between inputs. Then, after that, you can scan the robustness space, and so you also produce and evaluate designs, like in the sensitivity analysis. And based on this data, again, or here you will check the variation of the response in order to find out if you exceed your limit that you fixed, and if you see maybe that you really exceed a limit, you might go to the second or to this next step to really identify the most important scattering parameters, which means that you can use again the Metamodel, and this Metamodel will also give you the information about the sensitivities of your inputs. That means that you can really find out which are the critical input variations that lead to this exceeder, that lead that to the fact that you exceed your limit, and which inputs are safe, where you can even widen these input variations in order to save money. And yeah, this is actually the concept of the robustness analysis. So now we would like to show you some key features with the help of the examples we provided. So we will start step by step now with optimization of the diffractive beam splitter, which Michael will briefly explain.
Yes, so this is the setup which we want to investigate. So we have a light source which 632 nanometers, and what we actually would like to design here is the surface structure of this beam splitter. So we have, after all, a periodic structure. Here is the period. This has been fixed to define the positions of these orders already, and we would like to have a beam splitter with 6 diffraction orders, which should have an equal diffraction efficiency, and we would like also to have a restriction with respect to the minimum feature size of 300 nanometers. So this is the formulation of the optimization problem. We look at the efficiency, which I've said already. So this is the sum of the different orders, and this should be, after all, higher than 80%. And on the other hand, we have defined the uniformity error over all these different efficiencies, and this is our constraint. The uniformity error should be smaller than 0.5%. So this is already our setup. And of course, we want to maximize the total diffraction efficiency. In VirtualLab, we have the IFTA optimization algorithms for the design of such beam splitters. And this algorithm, inverse Fourier transform algorithm, is based on geometrical optics methods. And we can design the beam splitter, of course, and the efficiency which has been computed here for our design using IFTA is 84.5% and the uniformity error of 0.1. However, if we look more closely at the example, we will see that the computed feature size is around 500 nanometers, so it's small compared to the wavelengths. And that's why we are here requested to check the results with some rigorous method. And VirtualLab provides these methods, namely the Fourier modal method for analyzing such beam splitters. And we did this and observe and compute efficiency of 80% and uniformity error of 6%. And because it's a better method, this would be much closer to reality. And it also means that we have to apply here parametric optimization based on a rigorous analysis. Actually, this is also not surprising, this result, because the feature size is as small as the wavelengths, and typical handing wave rule is if the feature size is below 5 times wavelengths, then such a rigorous method and a rigorous check is required. And because of this, we can now switch to optiSLang and use here the parametric optimization for our setup.
Yes. To do this parametric optimization, we introduced 6 lengths, which correspond to this structure, which means we have here 6 intervals, and the scaling is such that the total length is equal to the period. So we have 5 parameters, since the total length is equal to the period. So these 5 length parameters we use, and also the scaling of the modulation length, which we call Z-scaling. So we have two input parameters, so 5 plus 1 input parameter, and based on that, we do now the sensitivity analysis. So the first step will be to identify the optimization potential by estimating the variation of the responses. And for this, we do the sensitivity analysis with an advanced Latin hypercube sampling to scan homogeneously the design space. So we vary these input parameters in this range, and you see that the designs are homogeneously distributed in space. So as a result, we found out, we used 200 designs, Latin hypercube sampling, and as a result, we found out that we have, that our objective is in a very small subspace, because only 4 out of 2,000 samples are close to this optimum. Because you see here that we would like to increase the total efficiency and decrease the uniformity error. And you see here only 4 designs. I will show you also in this post-processing of optiSLang. So we actually colored already the designs here. So you see the same, and you can now play around in the software also to change to different scaling, and the designs will still be marked in the color. And now you can use this for analysis. You might be able to reduce the input parameter space if you find out that only in a small part of the design space your best designs are distributed, and so on. So as a second fact, you can see that the objectives are not or only slightly in conflict, because you see there are some designs, because if there would be nothing in this optimal part of the design space, we would know, okay, it's not possible to achieve our aim. We would need to define 2 objective functions. But as they are not or only slightly in conflict, we might define the uniformity error as constraint. So the third fact, what you can see from this chart or this diagram, is that our variation range of the inputs was chosen in a suitable range to find an optimal design, because we are able to find an optimal solution even if there is further optimization potential, but at least we have some designs close to the optimum. So now we would like to understand and verify the dependencies between input and output variation. And for this, we used here the parallel coordinates plot, which can be used to understand relations between inputs and outputs, or outputs and outputs. If you don't know this plot, don't worry. We don't want to go into detail, but this plot really helps you to understand what's going on. So we actually wanted to see what happens for a high total efficiency and for a low uniformity error. And we saw that indeed there is something interesting, because the length L1 and L4, as well as L2 and L5, and also L3 and L6 are given, they correspond to each other somehow. So we therefore assumed that L2 is equal to L5 due to periodicity. It doesn't matter if we say L1 is equal to L4, or we just said L2 is equal to L5. and the others are also equal to each other. So by doing that, we could introduce only one parameter, which is called free length, instead of these 5 parameters. And to verify that, we established a Metamodel, and this Metamodel should also help you to understand the dependencies of input and output. And based on this Metamodel, we can estimate as well the noise level of our underlying numerical model. So you see here a COP matrix. So this matrix shows you this coefficient of prognosis I mentioned before. So you see for each line we have one response, and the most interesting part is now to see the total coefficient of prognosis, which is always nearly 100%, which indicates that our models are really good. So it was obviously okay to introduce this free length parameter. Furthermore, we see, because this analysis was based only on 100 samples, and which means this was really good to get very nice models. Before, with these 5 length parameters, we needed more samples to get nice models. And we can also say that the set scaling has only a small influence in general on all these responses. So these are actually the efficiencies for each transmission. And yes, so we see that set scaling has a small influence on this. We can see here, if we only consider the results, so the responses for the objectives, we can see it even better, that all responses depend on the free length we have seen. And what is also interesting is that the uniformity error is independent of the set scaling within this chosen parameter range. Because, or this means actually for us that we don't need to consider this input parameter for the optimization, because we can set the set scaling to the optimal value for the total efficiency. So here's the model for the total efficiency, and we can just choose the best value of this set scaling, and we don't need to optimize it, because it doesn't affect our uniformity error. And this I can show you also in our post-processing, just to see. You can see that here is what you have seen on the slides before, but yeah, it's a little bit more interesting to have a 3D look and to see this valley, and you are able to really analyze your model. You can switch to the other model and to go through all these models and to analyze them. Here we have only 1 or 2 inputs, so it's not so magic, but you can imagine that for many input parameters it will give you a really much more knowledge about what's going on in your design. What I also want to point out is that you find out by this total COP that your noise level of the underlying numerical model is less than 1% because of this very high COP, because the COP explains only the variation, or explains everything that is varying due to the inputs, but it cannot explain a noise. That's why 1% it cannot be explained, and that's why it must be noise. So now we would like to show you how you can improve your design efficiently. After you understood all these relations, you might want to select your suitable optimization engine. You want to reduce the input parameter amount and range. And of course, you would like to define reasonable objective functions. So, as I said, as this uniformity error is independent of the set scale, only the free length needs to be considered for the further analysis to find the optimum, because as it doesn't affect here this uniformity error. So we can actually reduce the input parameter amount because we don't need to consider set scaling. Furthermore, now we can consider the value of the free length in the optimum for the both objectives, for the total efficiency and the uniformity error. And we can see that the responses are slightly in conflict, because you see that the optimal value for the free length for the total efficiency is around 0.65, and for the uniformity error, the optimal free length would be 0.76, which means we have a slight conflict between these responses. So it's the best choice to define the uniformity error as a constraint. For the optimization. And which optimizer you choose, you will be guided by this selection tree, by this traffic light. Here, actually, this adaptive response surface method was predicted to be suitable. But as we are experts in optimization, we said, okay, also simplex method is okay. Which we have chosen here now. And we've used the total efficiency as objective function to be maximized. And as I said, the uniformity error was defined to be a constraint to be smaller or equal to 0.5%. And as a result, we received a total efficiency of 81.4% and a uniformity error which was very close to this limit of 0.5%. And these are the values of the inputs. Now we show you how this can be interpreted in VirtualLab.
Yes, of course, it's then possible to go back to VirtualLab with the results and to do a further analysis also in VirtualLab to use all the post-processing options and possibilities for computing further quantities in VirtualLab at the optimal position. So here you see, after all, the grading efficiencies in the above picture. And you also see, once again, we have used here an even order missing grading. So we have the working orders -5 to +5, and we have these other disturbing orders, including the zero order, which is shown here. And we have computed also the efficiencies for that. And below here, you see again how we could improve the design, starting from the IFTA design mentioned at the beginning. And here we have computed our target results based on a rigorous design method.
Many people might question now if we really catch the global optimum. And we can say here, yes, we did. Because as you have seen the charts or the diagrams already before, it was defined to have a uniformity error equal or smaller than 0.5%. So the free length that corresponds to this value gives a total efficiency of 81%. You see here in the diagram again. But you might say, okay, but I would like to achieve a higher total efficiency. But if you decrease this free length, you see here easily that the uniformity error will also increase. So This you can only understand if you don't use a black box optimizer. If you can really analyze your results precisely and tell your management here, I really did what I could because there's no more to do for optimization. I'm on the limit already. So, to sum up, we identified the dependencies by this beam splitter example by introducing this free length parameter. This was possible due to this parallel coordinates plot. We also excluded unimportant effects. This was here illustratively shown for the set scaling. We have already defined efficiently our objective functions to get a very efficient optimization. And our Metamodel of optimal prognosis explains the optimization potential for the question if we really catch the global optimum. As an outlook, you might imagine that we can adapt this problem to more complex tasks, like a 2D beam splitter, and also to identify and evaluate the critical input tolerances to do a robustness analysis. So the last part, the last example will be now the parametric optimization of an visible light gradient polarizer.
Yes, so in this example, we consider the optimization of a grating, and the purpose is to really polarize incident light, which is, let's say, it's elliptically polarized. We have this light in the visible range, and in the output, so after the grating, we would like to have a polarization state in X direction. So here again, we have the wavelength range in the visible range. We have a plane incident wave, and we have here the grating, for example, made of chromium, and we want to control the polarization contrast, which is defined in a minute, and of course also the transmission efficiency for the different components of the electric field. We want to optimize this grating, and here again the three parameters with the depth of the grating and the slit width of the grating. And the period is already fixed. The optimization goal is to maximize the transmission of the X component of the electric field and to minimize the transmission of the Y component of the electric field. So furthermore, we define the polarization contrast, which is the ratio between X and Y component, and this should be greater than 50. And finally, we look at the uniformity error of the polarization contrast, which is defined as given here. And this uniformity error is to be minimized. So to summarize this, we have one merit function which is to be maximized. We have a constraint concerning the polarization contrast, and we have a second merit function, which is the uniformity error.
Now the aim will be to define reasonable objective functions. By that we have done also a sensitivity analysis. So we varied again the input parameters. In this case it was the slit width varying in this range and the modulation depth. And we used 100 designs of advanced Latin hypercube sampling. Our objectives are the ones Michael explained. So you see, the first one was to increase or to have a polarization contrast higher than 50. I actually colored these designs in our post-processing in green that are have a higher polarization contrast than 50. So the other designs that have a lower polarization contrast, I colored in red. So we call these red designs infeasible designs. At the same time, we wanted to minimize this maximum efficiency in Y direction. For that, you can see easily that this maximum efficiency in Y direction is obtained for all feasible designs, which means we don't need to define anything else. So you see, because maximum, because only the green designs fulfill this aim to minimize this value. Furthermore, we'd like to maximize the minimum efficiency in X direction, which means we want to go close to this area here, because at the same time the uniformity error should be minimized, of course. And you see by the colored samples, or the colored designs, that there is actually no feasible design that fulfills these both objectives. And that actually also means that our objectives are contradicting. And for contradicting objectives, the method of choice is to do Pareto optimization, which means we have to define two separate objective functions in order to do a very efficient optimization. And you will see how this looks like to get a Pareto optimization. This will be now the part, and we briefly show you also our Metamodels we obtained, because these ones we can use now for a fast pre-optimization for this quite slow or for a noisy response. You see again here this COP matrix, where you see that our models are quite good for this total COP. And you can see also that only the minimum efficiency in X direction doesn't depend on the modulation depth. All the other responses depend on both input parameters. Here you can see the models. So the maximum efficiency in Y direction has this shape, and the minimum efficiency in X direction like that. It's kind of linear or quadratic model, quite easy model, simple model. But for the derived responses, we get very nonlinear models, which can be also easily approximated with this Metamodel of optimal prognosis. So you see that for the minimum polarization contrast, here is nothing happens in space, but in this area of the input space, it gets interesting. Furthermore, here is the model for the uniformity error, and this I will also briefly show you in the post-processing. It's the one. This one you have seen already. And this one I wanted to show you, like for the uniformity error. This will help you to analyze more deeply which areas of interest you might consider for further analysis. So, now, based on these results, we can use these Metamodels for the optimization, and this we actually did for this Pareto optimization. So we defined two objective functions, which is the minimum efficiency in X direction to be maximized, and the uniformity error to be minimized. At the same time, the polarization contrast should be higher than 50, and this was set as a constraint. So, as I said, we used the Metamodel as fast pre-optimization, and we got a chart of good designs, as you can see here. So, we actually have the Pareto front in red here. You get a front because we have no possibility to get to this area of interest, because the design or the objectives are in conflict. So that is very typical for Pareto optimization. So you see that because we would like to decrease the uniformity error and to increase this efficiency in X direction, so this has a negative, is negatively shown here. So this part is the region of interest. And as we cannot come closer, these are really the best designs you can get. So you see, we don't have only one best design. No, we have a chart of good designs. And now you as a user, you can select which design is the best for your application. So you might say that in this left part, you have a best design for your application because here the uniformity error is rather high, but the efficiency in X direction is rather high as well. At the same time, you might choose a design from this area where you have a very low uniformity error, but a quite low efficiency as well for the X direction. To analyze further in VirtualLab these designs, you might have a look on how actually these responses, these efficiencies are distributed referring to the wavelengths, and you might find out more in detail about your system. To sum up, for this gradient polarizer example, we efficiently defined the objective functions for very complex tasks by the help of the sensitivity analysis. We used the Metamodel of optimal prognosis for the optimization. Especially here, the solver run is very time consuming. And as you have seen, we did also Pareto optimization to get a chart of good designs, and because our objectives have been contradicting. In this case, you saw that we don't get only one best design, but a compromise of designs. Now we would like to invite you to get in touch with us for examples on these fairs and conferences, and also you are welcome to write us an email or to visit our website. I only want to briefly announce also our conference in Weimar, the Weimar Optimization and Stochastic Days in summer, in June. You're welcome to see Weimar in summer.
Okay, so thank you for listening